this. The thing is like some of the problems on 12.1, like you can still do them, but it sort of made more sense to do them after what I'm going to say about planes, which I will say either today on Thursday. So I felt like if I change I mean, they should be somewhat easy to do, but like if you prefer to wait until then like that's why I changed the deadline. And if I changed the deadline on 12.1, I felt like I should change the deadlines on the others, because it's weird to have the deadline for 12.1 to be after, the deadline for 12.2. So but yeah, usually I do change the dates, but typically throughout the semester, because if someone emails me and they ask for an extension and things like that, I just prefer to give the extension to the entire class than just like the student who asked me for the extension. So but yeah, like, but just because the deadline is changed, that doesn't mean you have to finish it the day of the deadline, even if it has changed. So it is but yeah, like typically that's like the reason why I changed again the deadline for 12.1, for example, and 12.2, because if I change it for 12.1, I felt like I should change it for 12.2. Yeah. But like in general, I'll do change the deadlines. Like the other thing I was going to say, well, also say see the participation like in return to normal levels. So it seems like the same capacity as before. So the like I will show you this. Like let's see if everyone can see the Firefox, right? So yeah, so what I was saying is like I changed the deadline for 12.1 to Friday, because by the end of, like, there's some questions about 12.1 which involve a little bit about planes, like very simple planes for which you really don't need to know what planes are. But if you can wait until then, if you want to do those. So since I changed the one for 12.1, I also changed the one for 12.2 and the subsequent ones just to make up for it. But all of 12.4, and like again, by the end of this week, for sure, I would say all these assignments you can finish without issues. And I already made available the remaining assignments, which will probably, I mean, I'll tell you more about the exam on Thursday, because by then, like, the official announcement should have been posted on the Canvas site. No, we have an exam in 2 weeks. Short exam. You didn't know this? Good moment. It is the first exam, yes. It is a short exam, so well, there will be an announcement that will be posted before Thursdays, which will describe the sections. We do have 1 short exam and 3 midterms. And so, but like in principle, I think it will go up to 13.3. Like that will be made for sure on the announcement. So so on Thursday we'll begin the class just by going a little bit over like what you should know about the exam. I just rather wait until the announcement is posted, but I'm just saying that definitely it would not go past 13.3. So that's why I already made available all the assignments like that you would need to work on the exam. Like not another one would be included. And also on the MyLab side, there's some old exams posted. But again, I'll say more about that on Thursday, because it doesn't make a lot of sense for you to try to do them right now, because you still need some more, like, we need to have covered a little bit more sections about the exam before you even try them. But I mean, yeah, there's some additional material that I will discuss on Thursday that you can also find on the Canvas side for the exam. But yeah, the first exam will be in 2 weeks from now. But I mean, it's it is like, hopefully it will be like emotional booster, because it is on the topics where people tend to do the best. So because it's it's like vectors and things like that. So we'll talk more about that on Thursday, if that's okay. But just, yeah, I'll let you know once the announcement, I'll post the announcement before then, before Thursday. And then we will go over the details on Thursday. Okay. But yeah, but in principle, if you want to work on all the assignments that could be on the exam, they're already available to you on my lab. At least that's like what I'm trying to say. So any other questions before we start? So far, so good. Good. Yeah, so today I just have to wrap certain things up that I have been avoiding, but let's finish this thing about cross product, and then I'll just mention something I had to say about that product which was left, which is this thing about projections, which I think some of you have already seen because I received questions about it. So let me share my iPad. Well. Before that, there's also a good thing that I don't know if everyone knows what GeoGebra, have everyone heard of it? Let me show it to you. Good. Can you see it now? This can be a very good friend for you. You can download it for free. It's like just geogebra.org or something like that. Just Google GeoGebra. I wrote the name on the chat. It's a great tool. So like, well, like very simple things it can do like this. So it's nice for calculus, like one variable, if you wanted to like see the graphs of functions quickly. But the cool thing is that it actually goes 3D to the 3D world. And this will be very useful, not at the moment. Oh yeah, Desmos. I prefer this over Desmos. It won't, but it is not that useful right now, but once we talk about integrals and other things, it becomes really useful. So for example, x equals 3, like x equals, and actually this we'll talk more about when we talk about planes, but if you look at x equals 3, it is a plane. Like I'll explain this between today and Thursday. It is actually, that actually looks like a plane when you plot it in a 3-dimensional space. And so if you take like y equals 8, you get an or let me make a smaller number so that it is easier. If you take y equals 8, you get a different plane, and then you can even change its color. Let me try to do this quickly. And so you get like, you see here like very clearly like the intersection of these two planes is like, should be like a line. In general, like the intersection of two planes is a line. So yeah, so those are things about planes, but like even like if you want to plot like the equation of a sphere, it can do it. And again, we'll talk about this more like in a couple of days, definitely before the exam. And if you want like the equation of a cylinder, it's actually like what you would call like a circle before, but it's just like a circle becomes promoted to like a cylinder when you look at the same equation in 3 dimensions. Okay, and so like, if you want to help to improve your visualization skills, this is like a very useful tool to use. I suppose Desmos like has a similar purpose, but I find it like this one very easy to work with. You don't even need to like download it. Like if you go to their website, you'll find like, let me just show you this also quickly. So if you go to if you go to geogebra.org, hopefully everyone can see it. Like this is where you can download it if you want, but you can also just type things that you are interested in. So it's like similar to like there's some, you can, like if you want to know about tangent lines, then you can find like apps or applets that people did using GeoGebra for showing like tangent lines and things like that. So it has many useful tools. And like that probably, I don't think I'm spilling any beans because I think all of you have seen this before. Like there's or the majority, like obviously like Wolfram Alpha, right? Which is also very useful. But this is more like for algebraic stuff, I think. You can also use it to graph things, but for that I just recommend GeoGebra. But like if you want to find like, you know, partial derivatives, which we'll talk about later, if you just want to check like a partial derivative that you computed, this is like a very easy way to double check certain things, right? So and even like you can, if you want to find cross products, which we'll talk about, this is what I'm going to talk about today. If you want to find the cross products between two vectors, this is like the interpretation that Wolfram is giving you. So you're taking this cross product and like this is the answer, and this is how more roughly the vectors look like, and other things. Is that okay? So just to keep in mind, you can also do dot product, but in that case, you should get like as a number. Is that okay? So good. Let's talk about then cross product. So yeah, let me, before finishing giving you like the formula for the cross product, let me just tell you how to find determinants. It's not that difficult, but so if you have like a 2x2 array, which is also another name called for a matrix. So something like this is called a matrix. Like this is called a 2x2 matrix. Sometimes you call it like big A. Usually the name for matrices are like capital letters. So like A here stands for matrix. And the determinant of A, which the book also, like sometimes you also write like this, like an absolute value of A. Or some like these are like the ways in which typically it's written. Doesn't matter too much. Like I'll like just tend to write like just this like det of A. This is just by definition, like what you do is like multiply the diagonals. So you multiply the entries of the diagonals with each other. So there's a diagonal here, you multiply these two entries, and there's another diagonal here. So you multiply those two entries, and that just gives you AD minus BC. So here, like the important thing to keep in mind is that you sort of subtract the result, okay? So for example, if like the matrix A is 2, 1, 5, 7, then the determinant of this matrix is what? 2 times 7 minus 1 times 5. So this is 14 minus 5. This is 9, right? And if A is a different matrix, like let's say 2 minus 4, 5, 6, this is 2. Sorry, the determinant for this one would be 2 times 6 minus -4 times 5. So remember, like the important thing here is that there's always a minus from the formula. So since this entry has like a minus sign, like minus minus becomes plus. So it actually ends up being added together. So 12 plus 20, which is 32. Are these two examples okay? Is it making sense? So far, so good. And again, if you take linear algebra, there's actually a lot of time that you would spend like learning about matrices and determinants and other things. So we won't really try to like get into the weeds. I'm just trying to give you like a bird's eye view, like the survival guide to determinants. Like this is what you need to know about determinants to survive this class. So really like things are just being treated as a little bit of a black box. I'm just telling you how to find it without going many details of why this is defined the way it is and things like that. But there's like a justification for why it is done this way. Okay. Like what I said last time, if you wanted like an interpretation of what this determinant is computing, is that if you have two vectors u and v, and another vector here v, which is I hate it when this happens. Resurrected. Is that okay? Can everyone see it? Now I'm paranoid. Right, if you have two vectors like this, u and v, you can sort of make the parallelogram. Um, and it has an area, right? And I don't know if anyone remembers from last time, like the formula for the area is actually, you can find it by just computing the cross product of those two vectors, which I still have to tell you how to do it in an easy way. But you would find the cross product of those two vectors and take its size, okay? But the other way in which it can be computed in this particular case is that it is really the absolute value of the determinant. So this is just the like as absolute value of determinant of A, where A here is a matrix A, B, C, D. So I'm just saying this is AD minus BC in absolute value. So for a 2x2 matrix, what you can think is that sort of like each row of this matrix specifies a vector, right? And then the determinant gives you, in absolute value, the determinant will give you the area of the parallelogram. Is that making sense? So that's an easy way to find it. Okay. Now comes a more interesting case, which is a 3x3 matrix. Okay. And this is really what we need for me to give you the formula for the cross product. So let's talk about a 3x3 matrix. So if you have a 3x3 matrix, it's something A, B, C, D, E, F, G, H, I, right? Like it's just like you're just going to put like 9 entries into this thing, right? It's 3x3. Now, really, like again, the determinant is going to be a number. So it's just a number. The way in which it is found, if you want it, is that essentially it's something similar to what I did before with this example. Let me see if I Uh, okay, I'm trying to make a box. I don't know if everyone can see it, sort of. Bad picture. Like, like in the same way which you can talk about parallelograms, you can talk about parallelepipeds. That's a complicated word, right? But I don't know if you see it here. Like I'm saying, like you could imagine like
Is it kind of like you got a bunch of typical parallelograms stacked on top of each other?
right. Yes,
Doing?
like taking a parallelogram and dragging it with the help of a third vector, right? So it is like this is such a bad picture. I think I messed it up when I was doing. Okay, like now it looks better if I put it here. Yeah, this is sort of like the base parallelogram, right? Like the one that I'm coloring. Something like this. And then with the help of a third vector, right? You sort of move it three-dimensionally. Is this better now?
Yeah.
So what I'm saying is that here you could think of why am I trying to make this? So this is a box or like a tilted box. Right. Yeah. It's like two parallelograms, like with their corners connected. That's a good description. So tilted box or parallelepiped. And the point is that, like, as you can imagine, this has a volume, right? So it has it's a container, and the volume of this thing, the volume V of the box equal, in fact, actually, it will end up being the same as the absolute value of the determinant of this 3x3 array. Where you think here that U is like, again, like A, B, C, and V is like D, E, F, and W is like G, H, I. So when you have three vectors in space, right, each vector has size 3, so 3x3 equals 9. So you can sort of arrange the entries of the vectors into a 3x3 matrix. And I'm just saying, if you take the determinant of this matrix and its absolute value, that will give you the volume, actually. So this is like the absolute value of the determinant. So like what this is saying is that determinants somehow appear when you're trying to find volumes or areas. And we will use this later when we talk about integrals, because, well, I don't know if you already did like integration with polar coordinates, right, in Calc 2. I don't know if you remember that you would write like something like, when you did an integral in polar coordinates, you would write like an integral like this of r dr d theta, right? Sorry, r d theta, or what, like, or r squared over 2 d theta, whatever. Well, it depends on how, like, what I'm not saying this very well, but like what I'm saying is that when we do we'll do something called double integrals, like, things like this from Calc 1, but we'll later study things like this, like in this course. But sometimes it's not convenient to do the integrals in terms of x and y. And so sometimes we'll want to do like an integral in polar coordinates. But the point is that in polar coordinates, you just don't write dy dx. You have to write, like, instead of writing dr d theta, you also have to multiply this by an r. And this r comes from some determinant. It's really called, this is secretly found as a determinant of something. this is computed as a determinant of a matrix. So this comes from a determinant. But again, this will make more sense later. Because the point is that when you switch coordinates, you sort of have distorted how areas and volumes look. So you have to keep track of the distortion with a determinant factor. Okay, but like somehow this is related to how you did in polar coordinates. You know, I'm sure you remember that in polar coordinates, there was like a factor of r or r squared over 2, depending on how it was explained to you. But it's sort of coming from a determinant. Okay, but that's let me give you now the formula, the black box formula for finding the determinant. So again, there are many different ways, but here's like the method for finding the determinant. The idea is like, so again, you have like this array A, B, C, D, E, F, G, H, I. And it's like one of these games, I think it's checkers, or one of like, imagine this like being colored, each square being colored with two, like you have two colors, like black or white or plus and minus. And so you're going to color each side with one of these two colors, but alternating. So like what I'm trying to say is that we always, like on the top left corner, we always begin with the plus color or the plus sign. And then we, from there, we just propagate. And so when you switch to the other entry, you just change it. So from plus, you go to minus, and then you go to plus again. And then from plus, you go to minus, and then you go to plus again. And then from here, from minus, you go to plus, and then you go to minus. And then from here, you go to, from plus, you go to minus, and then you go to plus. So just imagine that next to each entry, you put like a sign, like an extra sign. Okay. So why do you do that? Because like the formula for the determinant, for example, is the following. Again, there are different ways to explain it, but take the first row, okay? And from the first row, you extract the coefficients with the corresponding, with the new signs included. So this is like plus A minus B plus C. Is that making sense? Like, because only in the first row, only really one of the two coefficients would have changed its sign, which is the one in the middle. So far, so good. So you sort of remove them. And what do you do next? What you do is like, okay, where is A located? A is located in the first row, first column, right? First row, first column. So imagine just deleting the first row, first column of this matrix. What do you get? You get a 2 by 2 matrix, which would be this block. Is that clear to everyone? Let me just. And that's a 2 by 2 array, and for which you know how to find the determinant. So what you do in the next step is like, you just multiply A by the determinant of that array. So you just E, F, H, I. Okay. In fact, I mean, since we're going to work with the first row always, like the thing is that you can do this for starting from any row or column, but for our purposes, it's just sufficient to do this or with the first row. So like, let me just write it this way. So when you delete the first row, first column, you get this 2 by 2 thing. Yes. So for B, let's see, for B, like you're deleting first row, second column, so you get D, F, G, I, correct? D, F, G, I. And for C, it's first row, third column, so you get D, E, G, H. And that's it. And this will be the determinant. So let's do it in some examples so that you see how it actually looks like. That does it. And like the point is like a 4-4, like if you want to do it for a 4x4 matrix, it's sort of similar. You would take the first row of the 4x4 matrix, you extract the coefficients, like changing from plus, minus. And then when you delete a row, now you get like 3x3 blocks and you find the determinants of those. But then like to find the determinants of those 3x3 blocks, you do like something similar. So you see it sort of keeps growing in size because you always have to be referring to no, like the coefficients, right. The coefficients we make the coefficients of these 2x2 things, you just keep them the same. Right, that's why I deleted like that's why I deleted the plus minuses from the other entries because it could be confusing. What I was trying to say is that like there's really like a formula where you can expand the determinant through the second row. And if you expand the determinant through the second row, so you have to extract the coefficients with their appropriate signs with this flipping technique. But for us, we're always doing it from the first row. So that's all that you need to change. Yeah. So let me do it like, let's do it like with an example. Yes, correct. Let's say that that's your matrix. So what's the determinant of this matrix? Again, since we're always going to use the first row, you do this plus minus plus thing, just apply to the first row. So this becomes plus 1 minus 2 plus 3. Okay. And then now we have to put determinants of things that we obtain by removing rows and columns. So what do we get by removing the first row, first column? You get 4, 5, 2, 2, right? For the second and matrix is you have to remove the first row, second column. So you get negative 1, 5, 7, 2. And for the last one, you remove the first row, third column. You always remove the row and column where this coefficient belonged. So you remove the first row, third column, so you get negative 1, 4, 7, 2. Negative 1, 4, 7, 2. Is that making sense? Are there any questions about this? If you believe this, then you're done because now what follows is not that bad, right? Oh yeah, so now we can, so it gives you 1, right? What's the determinant of the, now this is the determinant of a 2x2 thing. So this is 4 times 2 minus 5 times 2. So you just get 4 times 2 minus 5 times 2, right? Minus 2 times, what's the this determinant? It gives you negative 2. Yeah. Good. Minus what? Minus 35. And this one gives you plus 3. And this is negative 2 minus what? Minus 28, right? Is that making sense with everyone? Is this okay? Well, again, the determinant, it will, like for us, will come soon because like you can express a cross product in terms of the determinant. So that's what I'm about to write after I finish this example. That's our main purpose for the determinant. So this gives you what? 8 minus 10, which is negative 2. And then it's minus 2. And this is like what? Minus 37. And the other one is what? Plus 3 minus 30. And so this is -2 plus, what is this, 74 minus 90. And what is this number? So it's
-18.
oh, good. Thanks. Is that okay with everyone? And this is an okay. This is a great example by accident because that's what's not my original intent. But this is negative, right? This is a negative number. The determinant can be negative. That's fine. But that means that in absolute value, it gives you the volume of this parallelepiped. It is lengthy. That's the thing, right? So that means that the absolute value of determinant, right? Absolute value of determinant, which would be absolute value of -18, which would be 18. That would be the volume of the parallelepiped that you would get if you use like the rows as the vectors for the box, right? This would be the volume of the box or parallelepiped obtained by taking the rows as vectors. Of the box. What is the difference? Yeah, you'll see there's a trick we have to do for the cross product. It's kind of a fun trick, but I'll write it right away. Yeah. This will be those two questions will be answered in a second. Is that okay? So far, so good. Are there any questions about how to compute the determinant?
This is fun.
Yeah, I mean, really, you take linear algebra, it comes in full splendor because here, like, you're just like, oh, it's like an acquaintance, right? Like, you don't want to give too many details of it. But it has many cute properties, like it's useful. It's just that we just have to like use it as a tool, so we cannot really spend too much time like focusing on it. But yeah, so finally to the question everyone wants an answer to, what's the cross product? How can you find the cross product here? Well, you say now cross product is between two vectors, right? So imagine that you have a vector u, which is u1, u2, u3, and you have a vector v, which is v1, v2, v3, right? Okay, you have 6 entries. That's more than 4. So clearly you cannot made it into a 2x2 matrix, right? The next step after 4 is 3, like after 2x2 would be 3x3, right? But you have 6 entries. You need 3 more, and so
would you just make them like 1 or something,
well,
or like 0?
Yes and no, because like the problem is that if you just make them actual numbers, you would get a number when you take the determinant, and the cross product is supposed to be a vector, right? So the trick is actually to cheat a little bit and put ij and k on the top. So what I'm saying is like you do this like this, and like right, you cannot agree to just put 111, for example, which could have been like a natural choice if you put 111 or something like that, because when you take the determinant, it would end up being a number. So you just like go with it and put ijk. And again, it's not really, it is less mystical than how I'm making it seem, because you can actually find the cross product in a different way, and then you realize that it coincides with the formula being presented this way. But it's just like to save some time that like I'm just summarizing what you would find if you do this like with more care. So this is like what u cross v equals. It's the determinant of this. Sorry, what I'm saying. That's what I'm trying to say. U cross v equals the determinant of this thing. And the point is that because you're putting I, j, and k in the first row, those are the coefficients multiplying the other determinant. So you do get like something in I, j, and k. So you do get a vector. See? Is that okay? Again, it is kind of mysterious, but I think in one of the YouTube videos, like actually there's one of the YouTube videos that I had recorded where I do actually explain why this formula ends up being true. So I can point it to you. It's like a 10-minute thing. It's just but it is less weird than it seems. So let's do an example. Let's do an example here where u equals like 1, 3, -5, and let's say v equals 1, 7, 2. So what's the cross product in this case under this interpretation? Is again a determinant of a 3 by 3 matrix where you put 1, 3, -5, 1, 7, 2. So you do need to copy them in this order. So it is important that u goes to the second row and v goes to the third row, because remember, I don't know if you remember from last time, u cross v is not the same as v cross u. There's a minus difference, minus sign difference. And this is actually can be seen from the determinant. Like if you switch the rows of a determinant, you get like a sign difference in the answer. And then here you put I, j, and k. Okay, and again, if you do this thing with the formula for the first row is plus I minus j plus k, right? Because remember the stuff about the signs. So it's plus minus plus. Oh, that's very Socratic of you.
Sir?
Yes.
I just noticed something. So we had to do this in statics, but like doing it now seems easier than doing it then. Why would that be?
I mean, but they gave you the same formula, I suppose, right? Maybe it's like when you see the same thing more than once, like it's sort of, yeah, just your brain just interiorizes the information differently. But I mean, presumably it is the given, they just wrote the same thing, right? I imagine the matrix trick. It's like everything is like a product, right? Like marketing, it depends on how you sell the determinants. It will look easier or not. So, but good that, I mean, it's better that it looks easier now, right? But yeah, it's 3, -5, 7, 2. Also, yeah, it's like there's an overlap between these classes, because like probably the beginning of this course looks a little bit boring to some of you if you have taken this before, but so this is sort of try to give some explanation for why things show up the way they do. So 1, 3, 1, 7. Is this making sense? Like how I'm choosing the coefficients? And then we're almost done. So this is I times what? What's the determinant? It's 6 minus minus, remember, becomes a plus, so it becomes 6 plus 35 minus j. What's the other determinant? Is 2 plus 5 in this case, plus k, and that's what? That's 7 minus 3, right? So it gives you 41. Usually it's very ugly to see the coefficients after the unit vector. So you just write 41i instead of I41. So just like that. And if you prefer, you can also rewrite it like this way as a vector. Is that making sense? So far, so good. If you did a cross product of this new vector with u and v, oh, you're asking, like, for example, you're asking, for example, what is like u cross v or something like that, right?
I was sort of saying, like, if you took this vector, this
Mhm.
new one that we just made, and crossed it with u and v, would you get like one or something?
Oh, like, well, it depends. Like when you say cross, like this is a single vector, right? Like what we obtain is a single vector, right? So do you want to take the cross product with u or with v or with u cross v? I don't know if my question. Well, but by both, you mean the third option then? Well, if you like, actually, this is and one that's easy to answer, because what's the what like, I don't know if anyone can tell me what this should be without doing any computations.
Is it just squared? The previous vector squared?
Well, it depends. Like, how would you mean by squaring? Do you mean like, right? Like it's actually zero, because remember that the cross product of a vector with itself is always zero. So because like you should not be confused by the fact that it looks like, you know, too many crosses everywhere, but like this is a single vector u cross v crossed with itself, right? So a vector crossed itself is zero. Yeah, is that making sense? Right, but like you can, they're actually called, if you go to Wikipedia, there are things called vector identities, where like you can find many formulas for like, oh, what happens if you keep doing cross products, or like, you know, keep playing around. Like, yeah, there are formulas for that, but we won't spend much time on it. Is that okay? Good. And so just to, we're almost done with this cross product business. In fact, like what I really needed to explain was that how to find it. So just one last thing before I forget it. Once you know the cross product, like say you can compute like the area of a triangle, that's also a useful formula to know. Usually for a triangle, you're specified the vertices or whatever. So if you have a triangle, P, Q, and R, this is also a formula you may see on some problems on MyLab. If you have a triangle with vertices P, Q, and R, what you can do, let me write it this way so that it looks nicer. So what you can do is like, you know, there's a vector here. I don't know if you remember the name of this vector. It's a vector that, for example, goes from P to Q. So it's a vector PQ, right? Called PQ. There's another vector here, which is a vector QR, right? Now that you have two vectors, you can make copies of them. So you can sort of make a copy of the vector QR, and you can make a copy of the vector PQ, right? And the triangle itself, Well, this other, I have made a parallelogram, but it is sort of naturally built into, comes from two pieces, right? Like from two triangles, each has the same area, right? So what I'm saying is that the area of this triangle with vertices PQ and R is 1/2 the area of the parallelogram with sides PQ and QR, right? Is that making sense? Is that okay with everyone? No, good observation. Yeah, it's not. You could also have used PQ and PR, for example. Yes, it ends up working, but it was just easier from the picture. Yeah, like there are variations that you can play around with the points. Like it doesn't matter. Yeah, there's some freedom on which two vectors you use for this. But yeah, this in the picture, this was the easiest for me to draw, and this just gives you and what's the area of a parallelogram is the size or the magnitude of a cross product. So it's just 1/2 of the size of PQ cross QR. Is that okay? So this is a formula for the area of a triangle that you will see used on the problems of the course. So far, so good. So like it's just compute the cross product. After you find a cross product, you get some vector, and the size of that vector divided by 2 is the area of the triangle.
You meant size of the area?
Sorry, I don't know what I mean. I meant after you take the cross product, yeah. After you take the cross product, you get a vector, and the norm of that vector divided by 2 is the area or the size of the area. Yeah.
Got it. Thank you.
Yeah. Good. So, just something that I forgot to mention. From 12.3. Oh, I didn't forget, but I just didn't want to say it right now at that moment because it's just not that important at that moment. But it back to 12.3. This is this stuff about projections, which some of you may have already seen questions about it on the online assignment. So it's an easy formula, but let me just tell you a little bit about vector projections. And so imagine that you have a vector u and you have a vector v. Like again, when I make pictures from vectors, I sort of try to make them in a way that that picture is the easiest to comprehend. It's not that v has to be longer than u or necessarily like, and like it doesn't need to be that v looks horizontal, right? Because if it doesn't look horizontal like this, then you just turn around your head, right? Like that's the thing about like the pictures, like you can sort of rotate your head so that the picture sort of looks a little bit closer to what I'm drawing. So it's just that it's more, it is just more pedagogical to draw them this way. And so the reason for doing it this way is that then you can think, oh, okay, imagine that you have like a light bulb or the sun, like on the sky. So here's the sun. Like then this is going to make like a shadow. This vector u is going to make a shadow along the vector v. right? So there's this shadow vector. Oops. And this shadow is called the projection of U along V. And let me just check that the name can look a little bit confusing. So let me just check that that's how the book is actually calling it. So yeah, this is a projection of U onto V, which is written like this. Is that okay? So let's find the shadow vector. So this is like, so in a sense, this tells you how much of this vector, you know, the shadow is sort of like what these two vectors share with one another. Like how much of U you can find on V. Like, you know, how, like in the sense, like if the vectors were orthogonal, right? What would you think the shadow would be if the vectors are perpendicular? You see, the shadow is just like a dot, right? It's zero. There's no shadow if the vectors are perpendicular. So that means that when two vectors are perpendicular, they sort of don't share anything in common from this perspective. So this is why sometimes you think of perpendicular vectors as having like independent information. If you think about it more like from a statistics perspective, they're sort of like uncorrelated in a way. They're because they don't have any data in common in a sense. So it would be this vector zero. It would be 0, 0, 0. Like you would still call it a vector, but it's just a point. So imagine that there was like an angle theta between these two vectors U and V, and the size of this vector, this shadow vector is called the scalar component. Like again, like I'm not a big fan of all these names, but the size of this projection is called the scalar component of U in the direction of V. Okay, so let's try to see how you can find both of these things. Okay. So let me draw again the picture because like I want to be able to refer to it. So let me copy paste that here. So here you had V. And here you had U. So the scalar component is the size of this blue segment. And so how can you use basic trick to how can you use trigonometry to find this blue segment?
I have a quick question.
Yes.
Wouldn't that blue segment just be the horizontal component of U?
Yeah. Right. Yes. Well, I mean, it is misleading. Okay, it is misleading in the sense that like the thing is like if V looked like this, right? And you still have U here. So the V no longer looks horizontal, right? This is still the scale, like, you know, that's still the,
So it has to fall onto the vector.
right, exactly.
Got it. Okay.
And just to answer the other chat question, right, this actually, secretly, the point is that you should think of this vector V as giving you some sort of like line. So in fact, as determining like some sort of line. And so really, if the angle between U and V looked bigger than 90 in the picture, like something like this, then the shadow just points in the, just happens to point in the other direction. Is that okay?
So is what we're trying to find, like, are these two vectors working together? And if so, how much are they working together, or how much they're
Right.
working against each other?
How much of U, I mean, the way to say it is how much of U is sort of contained in V, or how much, yeah, it's a little bit, like the point is that like my point is that the formula that I'm going to give you sort of works regardless of how you got drawn the picture. It's just like, you know, it's easiest to think of the picture like in the first version, but it keeps working in the other two versions that I'm writing. But yeah, someone like gave the right answer, like the cosine of theta would be what is the adjacent side, which is the blue one. Sorry. And then that's like, so that would be the size of this scalar component, which is the size of this projection vector, right? Because remember, this is the projection vector. So this is the size of the projection vector divided by the hypotenuse. So this is divided by U. Okay, and so is that making sense? And so that gives you like a formula for the projection, for the size of the projection. Let me write it here below. So far, so good. I'm just multiply both sides of the equation by the norm of U. Is this okay?
Yep.
But here's the thing. It's fine to leave it as cosine of theta, but the point is that we want to write it in such a way that you only see dot products. But remember that the cosine of theta, it is given in terms of the dot product, because like also here, U dot V, remember, is normal V times normal V times the cosine of theta. So here you can use that equation to solve for the cosine of theta. And so you end up getting the formula for the size of the projection vector, which is that, oh, let me do one more step. So from here, you get normal view times cosine, but cosine is U dot V divided by normal view times normal V. And you see like the norms of U cancel. And finally, you end up with this formula, which is the one that you need to know, that the projection is size, the size of the projection is U dot V divided by V. Is that making sense? So that's the size, that's the length of the shadow, like the size of the shadow. Is that making sense?
Professor, the absolute value on the bottom is U, right?
It's B.
Okay, thank you.
Yeah, sorry. I should try to make them more pointy. Yeah, because like the U's were the ones that canceled. The absolute values of U were the two that canceled. So like the notation is sort of nice because V appears here at the bottom, and it's sort of also what shows up at the bottom here in the formula, right? And just to finish, and I'll do an example in a second, but just to finish like the idea. So we already pinned down the size of this vector, right? We already know the size of this vector. And if you think about it, this projection vector, this projection vector is, you see, it's just like a rescaled version of the green one. It could be, in this picture, ends up looking smaller, but it could also be bigger, right? So it's just taking the bigger one and rescaling it by some factor, right? So that the length ends up being the same as this one. But so one way to think about this vector is that if you don't want to mess up the length, is that for any vector, you can divide it by its size and you get a vector size 1. So here's a vector v divided by its size, right? So this is called a unit vector in the direction of v. So this one has size 1, right? And so if you knew already that the shadow has size 10, you only need to multiply 10 by this unit vector, because that makes the unit vector 10 times bigger, you see? So basically the shadow is just like a rescaled version of the unit vector, and that scaling factor is just the length of the shadow. So what I'm saying is, like, what I'm trying to say is that the projection of u along v is essentially the vector v divided by its norm multiplied by this rescaling factor, which is the one that we just found. So it's u dot v over norm of v. So you just took the unit vector and made it however bigger or smaller it was needed, it was necessary. And that's the formula, and that's the other formula that you need to know for this part. So I'm about to do an example, but it is not so it's just the dot product of u with v. If you like, usually this is the way in which is how it's written on the book. So it's like you do the dot product between u and v and then divide by the norm of v squared. Is that okay?
Yeah.
So let's do an example. I mean, we have only 10 minutes, so it's not that we have that much time, but at least we do have enough time to do an example with this. So
wait, I have a question.
Yes.
Shouldn't there be another V?
Oh, good. Yeah, I forgot. At the end, you mean in the numerator? Excellent.
Yes.
Thank you. Yeah. Good. So you do the dot product between u and v, divide by the norm squared, and in the end, you multiply that by v. Good. Thank you. And now it's better.
Wait, quick question.
Yes.
Can't you just remove the v squared on the bottom and the v and just be left with u dot v over v?
Well, but if you do, okay, if you do that, you go back to the formula that we had here, right? Which is okay, but that's for the size. It's not a vector, right? If you wanted the actual vector,
Okay.
yeah. So that's the difference between this, right? The difference between this formula and this formula is that here it has like the bars. So that's just, this one is, the first one is just giving you the size. Yeah, but that's a good point. So
Thank you.
sure, like, so let's say u is like 2, -1, 5, or 3. And v is like 1, 5, 7. Again, I don't even know how these vectors really look like. Let's not worry too much. What's the projection vector like? Well, again, it's just u dot v divided by v squared times v. So what's the dot product here is like 2, -1, 3 dot 1, 5, 7. And what's the norm squared? That's 1 squared plus 5 squared plus 7 squared. So the numerator gives you 2 minus 5 plus 21. And this one gives you what, like 26 plus what's 7 times 7? That's 49, hopefully. And this is what? 18 over 75. Is that making sense?
Yeah.
That's a projection. It's not, and you see, like the point is that this projection vector, if you look at it, is just a rescaled version of the vector v, which was 157. So it's better to write it this way because, I mean, instead of just multiplying 18 over 75 in each entry, because this way just you realize that it's really just like a rescaled version of the vector v. And what would the shadow be? Well, in this case, sorry, what's the length of the shadow? Well, you use the other formula. It's basically the same thing that we just computed, so I will just write it more quickly. It's the same. It's essentially the same numerator that we had because it's the same dot product, so it's 18. But it is, and instead of dividing by the norm squared, you divide just by the norm, so it's root of 75. And that's the size of the shadow. Is that making sense? Which, by the way, is just obtain. I mean, once you know, this is actually consistent. Like once you just, it's the same as just like having taken the norm of this vector. Like, so, like if you take the norm of this vector, you get this. Yeah. So.
And so the length, so this shadow length, it acts along the v vector, right?
Right. Yeah.
That's why we're multiplying by a ratio that is like a smaller number,
Well, I mean,
or it could be a bigger number as well.
correct, right? It could just like because it really depends more on the line defined by v. So you just think that v itself has like a line. Actually, this is a good way to maybe end today's class, because let's say you have v here, right? And you have like the vector 3v here, right? And you have the vector u here, right? So how do you think the projection of u with respect to v or onto v is related with the projection of u onto the vector 3v? How do you think these two things are related?
They're the same.
They should be the same because, right, it doesn't really, it only depends more sort of like on the direction that v defines, but not how big v is, right?
Yeah. Okay.
On the other hand, let's do a similar picture now. If you had like, here you have the vector u, and let's say that the vector 3u is here, right? So what would the projection of the vector 3u would onto v be related? How should this be related to the projection of the vector u onto the vector v?
Oh, projection of 3 would be bigger.
Yeah, it's just like the shadow got 3 times bigger, so it's just 3 times the. Is that making sense?
Yeah.
Okay, so it depends. By previous equation, do you refer to this one or to this one? Like, so this one is just like the length of the shadow, and this one is not just the length, but the full vector. It's the vector, I mean, it has the direction incorporated into it. So this is actually giving you a vector, And this is just giving you the size of this vector. Good, good, yeah. Are there any other questions about this? Okay, so what we will do next time, we'll start talking, I mean, we'll talk this, we still have 3 minutes, so we might as well use them. So next time we'll talk about lines and planes. This is actually like one of the important topics of this chapter. Usually this one, like, there's always like, it's something that always appears somehow because it's like a useful, like you'll see it like, at least like, in all the exams, it's always, there's like one of these things that always show up. Like it is sort of like what we would have been building momentum towards. Like it's sort of like the culmination of this chapter, like 12. Because it includes cross products, it includes many other things. So like, so in 12.5, which is next time, so this is a big topic, an important one. We'll talk about planes and lines. And well, the thing, lines you already know, I think that's less, I suppose you have worked less with this. You have worked more with this, like, so lines are here, but planes, like those, maybe those are more like newer creatures, and you should think of them just like as infinite pieces of paper. Okay, so these are like planes. And what we'll find is that, well, you know, we sort of know how to describe a line. In high school, you saw it like y equals mx plus b. There's a little bit more geometric way to say this again. Basically, for a line, what we will do next time, a line is easiest to describe just by knowing a direction of the line, which is a vector. So for us, lines will be described by knowing, by just giving a vector, which gives you the direction of a line, plus a point, because you need to know also where the line goes through. So a line is described by knowing a point plus a direction. And what we will do next time is that it's, for the case of a plane, we'll see that for planes, it is easier to describe them. It is easier to describe a plane by just knowing a vector that's perpendicular to the piece of paper. This is called the normal vector. So this is the normal vector, n, which is just perpendicular to the plane. But I don't know if you remember, how do you find vectors which are perpendicular to something? That's where we'll use a cross product, right? Because if you know two vectors on the plane, right? Two vectors.
Wait, would it be cross product or dot product? Because if it's dot product, wouldn't it just be 0 if the
No,
vectors?
there would be, sorry, if you take, what I'm saying is that if you draw the two vectors on the plane and take their cross product, right? Then,
Oh, okay. Yeah.
this will be like the normal vector. So that's
Perpendicular to
how,
the plane.
right. That's how we'll find them in practice with the cross product. That's why we had to talk about cross product before this section. But like, so what I'm saying is that in general, like the normal vector, the plane will be described in terms of a normal vector and a point the plane goes through, because you still need to know where the plane passes by. So we'll start with planes next time, because that's probably a little bit more important than lines. So a plane will be described by a normal vector plus a point. Okay, so we'll talk about that on Thursday. So yeah, I'll see you on Thursday, and we'll do 12.5 next time, and maybe we have time to start 12.6, and that would be the end of chapter 2. Okay, good, see you. You too. Bye.
Thank you, Professor. Have a nice day.
You too. You
Thank
can
you,
always
Professor.
email me if you have questions in the meantime. If someone cannot show up to office hours, by the way. Yeah. Tariq already sent you an email about the office hours also. He has some